Welcome to the debate. So imagine trying to comprehend, the sheer destructive mechanics of a massive, roaring hurricane, but you are only permitted to study a single drop of rain.
Just one drop.
Just one. You might measure its temperature, its volume, maybe its chemical composition with absolute precision, but you would have zero concept of the atmospheric pressure systems, the thermal currents, or, the vast interconnected storm that's actually driving it.
Right. So you are measuring a reality, but you are entirely blind to the actual context generating that reality. I mean, it is an incredibly localized, almost impoverished way to look at a complex system.
Exactly. And for centuries, that has essentially been the reality of human healthcare. We've practiced medicine by isolating systems. The cardiologist looks at the electrical rhythms of the heart, right? The endocrinologist measures fasting glucose. But right now, we're in the middle of a monumental paradigm shift.
The unprecedented integration of artificial intelligence into global healthcare and biological analysis.
Yes. We are talking about the multimodal fusion of massive biological data sets, analyzing literally everything from planetary genomic data to the constant stream of data from wearable sensors, all the way down to the microbial ecosystems in our gut.
It's the technological equivalent of stepping back and suddenly having a satellite view of the entire global weather system, rather than just, feeling the rain on your face.
Spot on. So the central question we face today is this. Does this multimodal fusion fundamentally democratize and revolutionize predictive global health, or do structural limitations like profound data skew, infrastructural divides, and the sheer nonlinear complexity of biology make this paradigm fundamentally precarious, essentially threatening to widen disparities rather than close them?
It's a massive question.
It is. And my position is that AI is a powerfully democratizing force. I mean, it leverages tools like federated learning, edge computing, and multimodal transformers to overcome historical barriers and turn chaotic biological data into predictive, life-saving insights for all populations.
And my position is that the foundation of this AI revolution is deeply structurally flawed. The curse of dimensionality, massive biases toward Western populations in our data sets, and extreme computational demands risk creating spurious patterns that will exacerbate global health disparities rather than solve them.
Well, to understand why this is a revolution, I think we have to slow down and just grasp the sheer volume of data a single human body generates. I mean, the body is an unrelenting data generator.
Oh, absolutely.
In just one day, you experience roughly 100,000 heartbeats. If you wear a continuous glucose monitor, it logs about 288 distinct fluctuations in your blood sugar.
Every single day.
Every single day. You carry 3 billion base pairs of DNA, and your microbiome is teeming with 39 trillion distinct organisms. Traditional medicine really has no choice but to isolate these metrics because, well, human cognition simply cannot process them simultaneously. But AI cross-references these streams orthogonally.
Meaning it looks at them across completely different categories all at once.
Precisely. It turns biological chaos into clarity. I mean, The Lancet recently estimated that this level of AI cross-referencing could avert 40% of preventable deaths globally.
40% is a huge claim.
Doing things a human doctor physically cannot do. It doesn't just look at a retinal scan, it looks at the scan while simultaneously reading the patient's genetic text file, specifically their single nucleotide polymorphisms, or SNPs.
Right, the genetic typos.
Exactly. It's matching the visual damage in the blood vessels of the eye directly to the genetic typos that caused it. Because it connects those dots, it predicts diabetic retinopathy 15% better than traditional clinical baselines.
I certainly acknowledge the massive scale of the data, and the capabilities of a model like Clip Health are genuinely staggering. But I come at it from a different way. We must remember that more data does not automatically equate to objective truth, especially when the foundation of that data is structurally skewed.
Skewed how exactly?
Well, we have to look at the raw material we are feeding these algorithms. Currently, 80% of our global genomic data is heavily Caucasian skewed. If we look at bacterial DNA analysis for infectious diseases, 90% of the reference databases skew toward gram-negative bacteria. The models inherently misrepresent the global majority.
The datasets are incomplete right now, yes, but they are expanding rapidly.
But until they do, they encode blind spots. And furthermore, human biology is defined by incredibly complex, nonlinear interactions. In statistics, there's a phenomenon known as the curse of dimensionality.
Right, the variable problem.
Exactly. Think of it like trying to find a specific suspect in a crowded room. If you just look for a face, you might find them. But if you start tracking every person's shoelaces, their thread count, the dust on their jacket, you just get overwhelmed by noise. When your variables, say tens of thousands of biomarkers, vastly outnumber your patient samples, the math begins to break down.
But that's assuming a linear.
The AI is highly likely to overfit the data. It starts finding spurious patterns that look mathematically significant but are biologically meaningless. This is not just some trivial mathematical error. It is a direct pathway to dangerous over-medicalization.
Well, let's unpack that point about biological complexity, because that is exactly where AI proves its indispensable worth. I agree, traditional statistical models absolutely break down when variables outnumber samples. But we aren't relying on simple linear regression here.
No, we're relying on deep learning.
Right. We are utilizing unsupervised and deep learning specifically because they excel at finding invisible patterns that classical statistics misses. Just look at what happened during the 2025 global dengue surge.
In Southeast Asia.
Yes, in Southeast Asia, researchers deployed variational autoencoders, or VAEs, alongside transformer models to harmonize massive heterogeneous datasets. Now, a VAE essentially acts like a universal translator. It takes wildly different languages, like the genetic code of the mosquito vector and the immune cytokine response of the human host, and it compresses them into a shared mathematical space, so the AI can see where they overlap.
It forces them into the same context.
Exactly. And by fusing that data, the AI identified a highly subtle vascular leakage pattern. And it did this 2 weeks before clinical onset. I mean, no human epidemiologist could process that multidimensional matrix of variables in real time.
It is an incredible feat of pattern recognition. I will certainly grant you that.
And it goes beyond epidemiology. Consider DeepMind's AlphaMents. It successfully cross-referenced 71 million missense variants with clinical phenotypes to flag pathogenic mutations on a global scale. Think of traditional medicine as trying to understand a symphony by only listening to the flute, whereas AI is the conductor, who not only hears every instrument at once, but understands exactly how the vibrations of the violin affect the acoustics of the cello.
That is a compelling metaphor, but it glosses over a severe computational hazard. If your conductor is hearing instruments that aren't actually playing, the symphony is ruined. Deep learning excels at correlation, absolutely. But without causal AI, specifically frameworks that utilize do calculus, these models easily conflate correlation with causation.
I think we need to define do calculus for the discussion, just to be clear.
Of course. So, traditional statistics asks, what happens when X is present? Do calculus is the mathematics of intervention. It asks, what happens if I actively do X or change X? It separates the true cause from mere association, and without it, predictive models fail in the real world.
But they aren't failing.
Well, the source material outlines a perfect example of this. In vast data sets drawn from Delhi, AI models found patterns that strongly linked certain biomarker trajectories to respiratory disease onset. But upon closer inspection, those patterns were entirely spurious. The urban pollution in Delhi was simultaneously causing the blood markers to spike and causing the respiratory event.
It found a confounder.
Exactly. Because the AI lacked a causal framework, it generated false positives. It assumed the smoke caused the fire rather than the fire causing both the smoke and the heat. This creates enormous patient stress and runs the risk of severely over-medicalizing populations.
Over-medicalizing in what way?
Take lean diabetes, which is highly prevalent in Asia. If an AI trained predominantly on Western metabolic profiles encounters a South Asian patient, it may completely misinterpret their biomarkers. It sees a correlation that doesn't apply to that specific biology and recommends aggressive pharmacological interventions the patient simply does not need. We are putting blind trust in an algorithm that doesn't understand why a pattern exists, only that it does.
I see why you think that, but let me give you a different perspective. If we dismiss these deep learning architectures entirely due to the risk of environmental confounders, how do we explain their robust cross-cultural successes? Take long short-term memory networks, or LSTMs.
The time series models?
Right. These are designed specifically to devour sequential time series data. Instead of just looking at isolated snapshots of your health, an LSTM reads your biological data like a book, chapter by chapter, remembering the context of what happened yesterday to predict tomorrow. LSTMs are currently predicting the Matsuda Index, which is a complex clinical measure of how well your cells open their doors to absorb sugar, essentially insulin resistance, from just 14 days of basic wearable data.
Just from smartwatch metrics?
Exactly. Heart rate variability, sleep stages, activity levels. And they are achieving 88% accuracy. Crucially, the Mayo Clinic study validated this accuracy across populations in the US, Europe, and Asia. That is not a spurious pattern caused by a local confounder like pollution. That is a fundamental biological truth being decoded across ethnic lines by AI, turning a consumer device into a clinical-grade diagnostic tool.
I'm not denying that isolated successes exist in controlled validation studies. An 88% accuracy rate for the Matsuda Index is genuinely impressive. But predictive accuracy in a study does not automatically translate to equitable global democratization. We have to confront the physical and infrastructural reality of deploying this technology worldwide.
I would argue that deployment is already happening, and it's happening rapidly through frugal innovation.
I'm sorry, but I just don't buy that. Let me tell you why. You are talking about foundational models that require exascale computing. Training these algorithms, like those analyzing petabytes of metagenomic data, requires massive, highly expensive GPU clusters. Low and middle income countries simply do not have this infrastructure.
But they don't necessarily need the clusters on site to benefit from the data.
We are looking at a world where 3 billion people face deep data poverty. And frankly, the industry's proposed solution to this bias is structurally alarming. Because real high-quality data from African or South Asian populations is scarce, developers are increasingly relying on generative adversarial networks, or GAND, to synthesize, to artificially generate African or South Asian biological profiles.
They are filling in the gaps.
You cannot algorithmically hallucinate genetic diversity to patch over real-world data poverty. If the actual biological samples don't exist in the database, generating synthetic variations based on assumptions introduces massive clinical risk.
I think hallucination is a fundamental misunderstanding of what GANs actually do. Synthesizing data via GANs is a mathematically grounded bridging technique used to handle class imbalances. It isn't guessing out of thin air. It projects minority representations into the training space based on rigorous existing distributions.
But it's still synthetic.
It's a stopgap, yes, but an effective one mathematically. But even if we set synthetic data aside, we are witnessing real physical democratization right now in low-resource settings. Look at India's B2 app.
The diabetes management platform?
Right. It turns a standard smartphone camera into a diagnostic tool to serve 5 million diabetics. That isn't a massive GPU cluster locked in a Silicon Valley basement. That is edge computing operating directly in a patient's pocket. In Rwanda, zipline drones are actively using AI to predict malaria surges.
Using weather data, I believe?
Weather data and mosquito DNA, yes. Before this, they had to rely on retrospective clinic data, always reacting weeks too late. Now the AI combines those data streams to predict the surge, allowing them to distribute nets and therapeutics preemptively. And during the 2024 Mpox surge, localized African AI models actually outperformed manual diagnostics. That is the very definition of AI democratizing health.
Using smartphones for basic diagnostic triaging or supply chain logistics like drone routing is a fantastic application of technology. I'm not debating that. But it is a far cry from the multi-omics, personalized medicine revolution we are debating. When we elevate the discussion to advanced biological analysis like polygenic risk scores, the infrastructural divide becomes lethal.
Lethal is a strong word.
But accurate. Because these risk scores are built overwhelmingly on weird data,
meaning Western, educated, industrialized, rich, and democratic populations, they frequently miss epistasis entirely.
Wait, pause there for a second. When you say the models lack the mathematical architecture to perceive African epistasis, I want to make sure I understand. Are you saying the AI is literally blind to it, or just bad at reading it?
It is effectively blind to it. Epistasis isn't just about having a specific genetic mutation. It's about how that gene behaves differently depending on the other genes around it. Think of it like a line of software code that executes completely differently depending on the operating system it's running on.
Okay, I follow you.
In African lineages, which possess the highest genetic diversity on the planet, these epistatic interactions are vastly more complex and entirely different from European lineages. A model trained on European data literally lacks the contextual architecture to perceive the interactions happening in an African genome.
Because it doesn't know the operating system.
Precisely. In the clinical result, we see highly inflated risk predictions, or worse, direct clinical errors, such as the widely documented transplant mismatches for South Asian kidneys. You cannot fix a biological blind spot with a smartphone app. If the foundational dataset is structurally blind to your genetic lineage, deploying that AI globally is dangerous.
I'm not convinced by that line of reasoning because the very architectures of these networks are evolving to solve the data silo and diversity problem without centralizing data. This is where federated learning fundamentally changes the equation.
You're talking about keeping the data on local servers.
Yes, but the mechanism is what's revolutionary. Think of federated learning like thousands of chefs trying to perfect a cake recipe in their own individual kitchens. Under this framework, hospitals in Brazil's SOS network or Europe's Gaia X project do not have to surrender or pool their raw, proprietary patient data.
Right, for privacy reasons.
Exactly. They don't mail each other their raw ingredients. They train the AI models locally on their own highly diverse populations. Then only the mathematical gradients, the specific tweaks and weight updates to the algorithm are averaged globally. The AI just collects the recipe updates. This strictly complies with stringent privacy laws like GDPR in Europe and the LGPD in Brazil.
It solves the privacy bottlenecks, certainly.
Technology safely. For instance, using k-means clustering, which essentially groups similar data points together into natural clusters without needing predefined labels, we can map microbiome enterotypes across populations. Through this, we see the Zoe app predicting precise glycemic spikes based on gut microbiome data for 10 million Europeans. We see AI guiding fecal microbiota transplants in Italy with an astounding 94% success rate. Federated learning allows us to crowdsource the world's biological diversity, correcting those exact epistatic blind spots you mentioned, without ever compromising individual privacy.
Considered the massive structural friction of global interoperability required to make federated learning actually function? The mathematical averaging of those recipe updates across continents only works if the inputs are perfectly standardized.
Which is a challenge, yes.
It's more than a challenge. The reality of global healthcare data is absolute fragmentation. Japan's electronic health record standards differ wildly from India's. Even within Western highly funded systems, the U.S. Epic system struggles intensely to map its data ontologies to Europe's Cerner or TrackCare systems.
It's a translation issue.
It's a massive translation issue. Epic might categorize a blood pressure reading one way, while Cerner categorizes it entirely differently. You are assuming a frictionless, standardized data landscape that simply does not exist. If the underlying data isn't harmonized, your federated model isn't learning universal biological truths. It is just learning and propagating noise.
That's an interesting point, though. I would frame it differently. The friction is real, of course, but it is not an insurmountable law of physics, and we are actively watching it dissolve. Doesn't the rapid emergence of global FHIR standards, fast healthcare interoperability resources, prove we are successfully bridging these ontological gaps?
FHIR is promising, yes.
It acts like a universal USB port for medical data, standardizing how systems talk to each other. Furthermore, we have open-source models hosted on platforms like Hugging Face's Biomedical Hub. These platforms allow researchers anywhere on Earth to align their datasets without being locked into proprietary software. We even have the WHO's AdaBot working across more than 100 languages, actively bridging the natural language divide in patient data collection. The interoperability challenge is ultimately an engineering problem, and the global community is actively solving it.
It is an engineering problem, yes, but one with profound human consequences if we get it wrong. When you look at the entire landscape we've discussed today, I want to be perfectly clear. The technological leaps are undeniably profound. AI processes biological complexity at a scale human cognition cannot match, and we both clearly agree on that capability.
Absolutely.
But my conclusion is that the foundational vulnerabilities of this paradigm cannot be brushed aside. The data sets remain heavily biased. The computational hunger of these exascale models is driving a wedge between the infrastructure of the global north and south, and the interoperability nightmares are deeply entrenched. We must be incredibly cautious. If we rush to deploy these systems globally without solving the root data exclusion, if we rely on synthetic data to paper over the fact that certain populations are missing from the math, we risk encoding those blind spots into a universal, permanent health paradigm.
And my conclusion focuses on the trajectory of this technology. Yes, there are growing pains, and we clearly continue to disagree on whether tools like synthetic data generation and federated learning are sufficient cures for systemic dataset flaws. But I believe AI is already an indispensable bridge transitioning us from reactive medicine to predictive global health. By democratizing biological insights through edge computing and global data fusion, we are no longer just treating the sick after the fact. We are actively anticipating vulnerabilities and averting millions of deaths before they occur. The capabilities are scaling, the barriers are dropping, and the benefits are becoming universally accessible.
It is vital that we continue to examine global health technology through both of these lenses, its maximum theoretical potential and its harsh structural realities.
Absolutely. And there is so much more to explore in this material, especially as even more advanced technologies like quantum AI for hyperparameter tuning and simulating protein folding begin to emerge on the horizon. Which brings us back to where we started. For the entirety of human history, we have been trapped looking at a single drop of rain, trying to guess the weather. The AI revolution has finally given us a map of the entire storm system.
The critical question remains whether that map is accurate for everyone on the ground, or just for the people who built the instruments.
And that is a question we must continue to answer together. Thank you for joining us.